Hi, thanks very much. I'm here to talk about scalable P2P clock synchronization with a mesh method for distribution. A little bit different to your typical P2P distribution. So we're here as part of the OCP TAP sub-project. We are all over in the Experience Center. There's a various sort of array of displays and live demos going on over there. You may have seen it in some of the emails that go out. Primarily the flagship is the OCP TAP time card. This is a PCIe format, which turns the server into an atomic clock, which is pretty cool. I think there's versions generation 1 through to generation 3 over in the Experience Center. And recently we've come out with the baby brother of the time card, which is what you can see there on the left, the black module there. It's a small form factor, sort of fits under a CM4 Raspberry Pi, if you're familiar with that. And then there's expansion modules currently working with companies like SciTime with their MEMS oscillators to sort of plop on, and you can really sort of start to customize how you use sync in these devices, both on the high end with the time card and also on the lower end with this sort of baby brother time card. And it's all in this goal to democratize time, make it accessible, make it open. All the plans are online. You can build them yourselves, as well as go to some of the manufacturers and get it pre-built for you. So where we're concerned, my name's Ian Goff from TimeBeat. We focus on the software side of PTP. And if you're not familiar with P2P, it's a method of disseminating time across a network. Traditionally, it's more accurate than methods like NTP, although not always the case. And historically, this is sort of your deployment model in a boundary clock based system. And what you have is a hierarchy of clocks from grandmaster through to a distribution layer and down to the end host. And each point of that, we believe, is a potential point of failure, ultimately, which is it's not ideal. And it's not always the most scalable. So we came up with a mesh-based structure, in effect flipping that, if I just go back quickly, flipping that on its head, so it's sort of many to one rather than one to many. And that creates a mesh table we can see here. So on the right-hand side is just a nice visualization for it. But essentially, we have a peer-to-peer distributed hash table, which seeks out, finds other peers in the network, all encrypted with key gens they generate themselves. So it's nice and secure. And it automatically sets up unicast sessions amongst the grid. We call the grid nodes, obviously, and then we have root nodes, which inject UTC into that environment. That allows for self-healing and auto-configuring mesh based on real-world network parameters. Some of the key issues with clock sync is the network itself, transportation of the packets. If it gets slowed down by a switch, an easy one to understand is if someone downloads a file, it starts to fill up that network and sync becomes a little less accurate than it should be. And then once we go on to the next slide, it'll make more sense. But with this method, we can do near lossless distribution, which is one of the keys to a multi-node system. If you're not going to take UTC direct from the source, you need to be able to get it to the end location without introducing lots of error. So, it looks like we've got one in between that one. So if we consider how well we can scale with this, if you consider a traditional grandmaster clock, tends to be around a 2,000 end node unicast sessions per device. Now, that's not overly scalable. So what we've done is slightly different. We've democratized the grandmaster, and we've included the host devices operate as grandmasters and followers as well. So they take the time and they give the time. So in this example, we're looking at each device using 2 sources of PTP for redundancy, and they send out 20 to 20 other hosts. And if we follow the maths, after one hop, you have 20, which makes sense. Then we have 400, 8,000, and 160,000 seats available. Divide by 2 because we know we want the redundancy. And that gives us 84,000. Now, That's not a huge amount, granted, but if you scale that up to the next hop, you've got 1.6 million devices being synchronized, all with negligible overhead, and all with this near lossless distribution. So it's all verified because you have the multi-sources. It's throughout the network, so different network hops, you can evaluate different like network topologies and sort of get to understand your network a little bit. And obviously it dynamically reconfigures, and you don't have to do a thing, right? 1.6 million hosts is a lot of hosts. So this is just a quick one, nothing too complicated here, but another viewpoint from our front end. Traditional PTP will look closer to those red dots. And we have filtering systems to enable this multi-hop nature. So we actually only use the blue dots to synchronize, which, although it might be a bit tricky to see on this screen, it's about plus or minus 5 nanoseconds, and that's on every hop. So you can consider every hop adds 5 nanoseconds. By the 5th hop, you're at about 20 nanoseconds, maybe the 15 mark if you get lucky on the plus or minuses throughout. But it's effectively as pristine as you can make it throughout that sort of system. And I believe that's sort of all I've got. If you want to talk more, my colleague is doing a deep dive on this at 2:40 on one of the breakout rooms, Lasse Johnson. We are also, as I say, in the Experience Center. Come over, have a chat. We have a live demo running. We have the hardware there as well. And yeah, any questions? I do have a couple of minutes here. If not, thank you very much. Thank you very much.